Okay, so this is 16.4, triple integration. So we're going to be integrating over regions in space. So solid regions is often what they're called. And we're doing, in general, the notation would be something like that. All right, so for example, maybe our region of integration now is the inside of a sphere of radius 3, for example. Okay, so not just the surface, but the inside. All right, so D might be, for example, x squared plus y squared plus z squared less than or equal to 9. All right, so the inside of a sphere of radius 3. Okay, so this is a triple integral because now we're going to be integrating with respect to, at least today, in this lecture, x, y, and z, right? So ultimately, we're going to be doing dy, dx, dz's, something like that. The idea behind the kind of mathematical fundamentals behind this is the same as with two variable and one variable calculus. So again, in one variable calculus, you're chopping your region up into segments, and you're adding up areas of rectangles. In two variable calculus, you're chopping up your region into rectangles, and you're adding up the volumes of rectangular boxes. And now what you're doing is you're chopping up your region, which is a region in space, into rectangular boxes. Right? So this is pretty much impossible to draw. And you're adding up values at each rectangular box. All right, so we're not going to be able to obviously draw a fourth dimension. This picture is really messy. So one rectangular box would be, integrating over this guy here, right? You want the volume of this times the value of the function. Just like up here in one variable calculus, you want the length of this guy times the height of the function. And in two variable calculus, you want, let me just draw the domain. You want the area of this box times the height of the function. All right. Okay, so we're not going to be saying stuff like in the previous section, volume under the graph of f, because this would be now four-dimensional volume as opposed to what we normally think of as volume. So a good way to think of these is perhaps in terms of mass, right? So we have a solid object like this sphere here, and we want to know the mass of this sphere where it has a certain mass distribution, right? So at each point in the sphere, there's a mass distribution. So that would be our function, f of x comma y comma z. And in order to get the total mass of this spherical ball, we would integrate kind of our mass at each point over the entire sphere. All right. So let's just get right into how to integrate. Because we're chopping our regions up into rectangular boxes, again, just as with two variable calculus, we can add up these boxes in any order that we like. At least in our class, we can. So essentially, that means integrating in terms of any order that we like, dz, dy, dx, or dx, dy, dz, or dy, dx, dz, and so on, right? There's 6 different possibilities. So we'll be integrating, trying out all the different possibilities when we actually start doing problems. Okay, so how do we actually do these? Well, if we integrate with respect to dz first, which is probably going to be our most common source of examples, in two variable calculus, when we integrated with respect to dy first, for example, let's say we were integrating over this region, we represent our dy integral as a vertical line, right? So this is the integral dy dx of whatever, right? We integrate our inner integral, we represent it using a vertical line, dy, and then we integrate from x equals this point to this point out here, okay? So now, same idea. If we integrate with respect to dz first, we represent that with a vertical line, right, in space, right? So our region is, again, a region in space, and we represent the dz integral as a vertical line from one end of our region to the other. Okay. All right, and then we do the dy dz. So let's actually do an example. So let's calculate triple integral, and let's do x cubed y squared z dv over the region D, where D is the solid in the first octant, bounded by the coordinate planes, the three coordinate planes. So that would be the xy plane, the yz plane, and the xz plane, and the plane x plus 2y plus 6, let's do 3z, equals 6. All right. Okay, so as with two variable calculus, you always want to draw your region. So this is going to be happening in the first octant, right? The boundaries of this solid are going to be the three coordinate planes. So let's draw them. So again, this is we're drawing our region. And this plane right here, x plus 2y plus 3z equals 6. So let's see. So this is the plane that it hits the x-axis when y and z are 0. So it hits the x-axis at 6. It hits the y-axis when x and z are 0. So that would be at y equals 3. And it hits the z-axis at 2. All right. So in terms of the picture, it's going to be this guy right there. All right. So that's our plane. We're integrating the region, kind of this tetrahedral region, again, bounded by this plane that's facing us right here, and then the xz plane, the yz plane, and the xy plane. Okay. So if I just draw the solid by itself, looks something like that. All right. Okay. Let me draw that again, just so we can figure out our limits of integration. All right. So again, as usual, we're going to figure out our picture using our limits of figure out our limits of integration using our picture. So let's decide to integrate with respect to z first. Okay. Our function, whatever it is, I'm just going to stick that in here, right? We're going to integrate z equals. Okay. So how's this going to work? Well, we represent our z integrals dz as vertical lines, right? Because we're kind of adding up these boxes in a vertically first. That's the way we can think of this. And each vertical line, you can see, in terms of our region here, always starts from the ground, right? And ends when we hit the plane. Okay, so this is going to be from the ground to the plane. All right, and you can see it's consistent here, always from the ground to the plane, from the ground to the plane, these vertical lines. All right, and again, these vertical lines are always, of course, we want to fill up our region with these vertical lines. And so in order to do that, where do our vertical lines have to live, right? Well, the way to figure this out is we use our idea of the sun shining from above, right, from the z direction, the light's shining down. The shadow that our region makes, right, that's going to be everywhere where there should be a vertical line, all right? And in this particular example, the shadow is going to be this triangle down here, okay? All right, so our integral, so our dz integral is from the ground to the plane, and then our next two integrals here is going to be over the xy plane, right? It has to be x and y because after we've done the inner integral, we've lost all our z's. It's going to be the xy plane, and it's going to be a region bounded by the x-axis to y-axis, right? This blue region here, bounded by the x-axis, y-axis, and then this line right there, all right? And that line is the one that passes through, so this is x, y, z. It passes through 6 here and 3 there. Okay. All right. So that's pretty much it in terms of our setup. You can see the way we've kind of done this is we figured out the z integral, and then the other two integrals is a two-variable a double integral problem from the previous sections. All right. So as usual, we always like to reduce our problems into ones we already know how to do. Right. So again, these outer two integrals is essentially something we already can do. So it's almost to the point where we don't have to actually talk about it. Okay, in any case, for this particular problem, let's set up the entire thing. So this, I didn't put dy dx or dx dy here because I think probably the best thing to do is once you've drawn the picture or figured out what your two variable integral is going to be, then you decide whether you want dy dx or dx dy. All right. So you first decide the dz, for example, and then afterwards you decide your dx dy dx. Don't decide it all at the beginning. Okay. Okay. In any case, our full integral is going to be, well, z equals the ground. That's just going to be z equals 0. All right. So this is going to be z. Oops. Let's do it like this. This is going to be z equals 0. And z equals the plane. Well, the plane is the plane up here, x plus 2y plus 3z equals 6. And so that's going to be z equals, just throwing everything else to the other side, 6 minus x minus 2y all over 3. Okay? All right, so our inner integral, our innermost integral, is going to be, so what was the function here? X cubed y squared z. All right, we're going to do dz, z equals 0 to z equals 6 minus x minus y all over 3. All right, and then the again, as we said, the outer two integrals, we just do it as a two-variable calculus problem. In this example, in terms of x and y. Let's do dy first. Right? And again, it doesn't matter, right? We could do it any way we like. For this particular problem, I've just decided to do dy first. Our y's are going to start at the ground, so y equals 0. And we're going to go all the way up until we hit that line, right? What's the equation of that line? Well, there's a couple ways to figure it out. Just from this picture, we know it's the line that passes through 6, 0 and 3, 0. So we can figure out the equation of the line from that directly, or we can look at the equation of our plane up here, x plus 2y plus 3z equals 6. This line that we're looking at right here is actually, in our picture, it's this guy. Let me do it here. It's this guy right here, right, in our 3D picture. And that's where our plane hits the xy plane, right? So in other words, it's where our plane, x plus 2y plus 3z equals 6, intersects z equals 0. So immediately I know the line is x plus 2y equals 6. All right. So this line right there is x plus 2y equals 6. All right. And again, you could figure it out from scratch just from these two bits of information there. But maybe it's more efficient just to use our plane and recognizing that line is comprised of the intersection of the plane with the xy plane. Okay, in any case, that tells me y should be 6 minus x over 2, right? Just solving for the y. And then we can see we need these vertical lines starting from, in order to fill out our two-dimensional region, our triangular region, x equals 0, all the way out to x equals 6. And we're all set. This is our setup for our integral. And at this point, you just do the integral just as you did two variable integrals. You integrate the inside first. With respect to z, think of x and y as constants, right? Plug in your limits of integration. That will kill off all the z's from the problem, and then you have a two-variable integral. All right. So for example here, I'm not going to do the entire problem, just the first step. Just reduce it down to a two-variable integral. So y equals 6 minus x over 2. We integrate this guy here. We get x cubed y squared. Again, we think of that as a constant. Integral of z is 1/2 z squared. We evaluate that at z equals 0. And z equals 6 minus x minus y over 3. I think that probably should have been a 2y, right? What was our plane? Yeah, x plus 2y. So this should be 2y there. That should be 2y there. And then dy dx. Okay. Okay, and then now we just plug in and we'll see all the z's disappear. Two, 1/2 x cubed y squared, and then we got 6 minus x minus 2y all over 3, whole thing squared, dy dx. And this just becomes a problem from 16.2 or 16.3 or something like that. All right. Okay, so ... All right, so essentially the idea is very straightforward in that it follows what we did in two variable integration pretty much exactly concept-wise. All right, now while a lot of the times we'll be integrating dz first, certainly we can integrate, like I said, in any order we like. So let me do the same integral in a different order just to see how we should set that up. Let's see. Let's do it down here. So we were looking at f of x comma y. I'm not going to actually do the integral at all, so I don't really care what the function is. Again, most of these problems, the new stuff is the setup, right? Okay, so the interesting plane we were looking at was x plus 2y plus 3z equals 6. We were looking at this picture here, x, y, z. This was 6, that was 3, and that was 2. Okay, so if we wanted to integrate in a different order, let's say we want to do dx first. Let's do dy first. I think it's easier to draw the picture this way. Let's do dy first. So f of x, y, z, right? If we want to do dy first, we want to represent our integral, the dy integral, as lines where only y is moving, right, just as usual, and x and z are constant, right? So these would be lines parallel to the y-axis. So just like up here, we represented our dz integral with vertical lines. Vertical lines are lines parallel to the z-axis, right? So now we want to integrate dy, so we want lines parallel to the y-axis. Because again, if you're parallel to the y-axis, moving along that line means y is changing, but x and z are fixed. Okay, so a typical line would be maybe starting here at y equals 0, and then we go all the way out until we hit our plane. Okay, we start at y equals 0, go out until we hit our plane. Y equals 0, go out until we hit our plane. And we can see it's completely consistent in that way. So it's always going to be y equals 0 to y equals the plane. All right. Okay, what is the plane? Again, x plus 2y plus 3z equals 6 is our plane. We solve for y, and we get 6 minus 3z, 6 minus x minus 3z all over 2. All right. Okay, now, what is the dx z or dz dx integral, the two variable integral? Well, this time, because we're integrating with respect to the dy first, right, we want to figure out for which x and z values in the xz plane do we have a line living above that. All right. Well, again, in terms of visualization, you can think of the sun shining from the y-axis, parallel along the y-axis, shining downwards. And anywhere where you see a shadow, anywhere where our region makes a shadow on the xz plane is where we want to integrate the dx, dz, dx. All right. So in this particular case, we can see that that's going to be that triangle right there, right? Everywhere on that triangle, that's going to be shaded by the sun shining from the y-axis, right? Or again, more mathematically, anywhere on this triangle, we're going to be integrating a dy integral from the ground to our plane, right? So for example, if we're out here, right, if we're at a point out here, we don't want to do a dx dz integral because it's not actually, no place along the y-axis hits our region, right? So we're not going to have any integral out here or out here or out here or anything like that. So it's only the blue shaded region. Okay, and what is the blue shaded region? Well, we can see that if this is 6 and that's 2 over there, we've got 6 here, 2 here. This is x and that's z. We're integrating over this guy right here. Okay. Okay, and of course it should be x and z because at this point when we're doing the two variable integral, all the y's should have disappeared, right? So make sure you've got kind of the variables correct here. Okay, and of course if we want to do the set up an integral in here, it's just a regular two variable integral. And so we can set it up, either with integrating dx first or dz first. Let's do dz first for no particular reason. This particular problem looks like it'd be just as easy either way. So if we do dz first, we can see z always starts from the ground until we get to the line. So z equals the ground, z equals 0, until we get to the line. And again, we can figure out the line just from the picture we have here, or we can look at our original plane. Our plane, the triangle we're currently interested in is where the xz plane intersects with our plane up here, right? The xz plane is where y equals 0. So the intersection is going to be x plus 3z equals 6, right? So this line right there is going to be x plus 3z equals 6. Okay, so that means we need to integrate from z equals 0 to z equals 6 minus x all over 3. And in order to fill this region up with vertical lines, we need to start at x equals 0. And we need to end at x equals 6. All right. And again, at this point, you just mechanically do the three integrals. As usual, thinking of the appropriate constant as appropriate variable as non-constant and all other variables as constant. Okay, if you wanted to do this dx first, then your point of view would be the sun would be shining along the x-axis, right, this way, and your two outer integrals, your two variable integral would be the shadow, if the sun were shining in this way, and it would be in this plane right here, and in this particular example, it would be, again, a triangular region in the YZ plane this time. Okay. All right, as usual, you always want to refer to the picture. If for whatever reason you've set it up in terms of dz, dy, dx, and you decide it's too hard, and you want to try dy, dz, dx instead, right, where the dy first instead of dz first, don't set it up from your previous integral, set it up from the picture. All right, it's really easy to make mistakes if you try to work without the picture. Okay, let's do another example. So basically the rest of this section is examples, because what we really want to get used to here is drawing pictures and kind of visualizing our three-dimensional region, because again, without the picture, it's really hard to get the limits of integration correct. Okay, so let's find the volume of the region of the solid. So I'll try to keep it where I say solid for kind of three-dimensional regions. Find the region, the volume of the solid above, that lies above the xy plane. All right. Inside the cylinder, x squared plus y squared equals 4. And below the plane, z, let's do it like this, y equals 2z. Okay. All right, so in terms of the picture, this is going to be everything. So we're looking above the xy plane. We're looking inside the cylinder. So this is our cylinder here, right? So we don't want the stuff out here. We want the stuff within the cylinder. And below the plane, y equals 2z. So the plane y equals 2z. So sometimes it might help to draw these things separately first, perhaps, because things do get a little messy. So this is our plane. This is our cylinder, right? We're inside the cylinder, but we're also below this y equals 2z plane. So the y equals 2z plane from the first chapter we did, right? You just draw the y equals 2z in the zy plane or the yz plane. So that's going to be a line, right? We stretch it out along the x-axis in order to get the full two-dimensional plane shape. Let me exaggerate it, draw it like that a little bit, and then we pull it out this way. All right, so it's going to be a plane that looks like that. Of course, it extends infinitely this way, and extends that way as well, this way, in all directions. Okay, however, we're only interested in the part above the xy plane, and we're only interested in the part inside the cylinder. So if we try to draw this all together, it's going to look like we have a cylinder here, right? And we're cutting it. Let me draw the other side as well, kind of like that, right? So we're cutting it with our plane. So our plane goes here, right? It's cutting. This is the x-axis right there, and then the plane is kind of tilted up this way, right? And it's cutting this, so it's going to cut it kind of in a shape like that. All right. So ultimately, our shape looks like a kind of like a doorstop or something like that. All right. Let me draw it by itself. Looks like this. Looks like that, and it looks like that. All right. Let me fix that a little bit. And let me fix this. Okay. So in this picture, this is our plane, right? Y equals 2z. And this side here is our cylinder. And the bottom of this, so the bottom is xy plane. Okay. So those are all the kind of the boundaries, the boundary surfaces of our solid. Okay. So this is the kind of information that you want when we need to set up the integral. Okay. Oh, by the way, so the way I've written this problem, right, lies above the xy plane. So sometimes you'll see a problem described in words in this way, or sometimes you'll see it described in terms of equations, right? So an alternate version of this problem could be, instead of lies above the xy plane, I would say solid where, instead of that, of course, where z is bigger than or equal to 0, right? That would say the same thing. Inside the cylinder, x squared plus y squared equals 4, I could say instead x squared plus y squared less than or equal to 4. All right. And then below the plane z, 2z equals y would be something like, below means, right, under, refers to the z-axis, right, up and down. And so that would be 2z, oops, 2z less than or equal to y. Okay. All right, so that would be an alternate way to state the same problem. So you'll see all the different ways in the homeworks and in the various sections in our class. Okay, in any case, no matter how you see it, right, you need to interpret it, draw pictures, try to draw, you might have to draw multiple pictures to kind of get it clear what's going on, and maybe sometimes rotate your picture a little bit to get a better kind of perspective as to what your object looks like. Okay. All right, but in this particular case, I'm pretty satisfied with this picture over here because I can see all the components of my of the boundary of my region. All right. Okay. So let's set this up. So if I want to do this dz first. All right. So triple integral dz and then dx dy dx. The function we're integrating, so we're finding the volume of this region, right? So that means the function we're integrating is just 1, right? Just like when we wanted to find the area of a region, we integrate with respect to 1. And when we want to find in two variable settings, and in one variable setting, if we want the length of a segment, right, we integrate 1 from a to b, right, and we get our length, b minus a. Okay, so the volume now is the integral of 1, all right? Okay, we're integrating z first, so z equals something to z equals something. If we look at our picture up here, integrating with respect to z means vertical lines represent the dz integral, all right? Vertical lines parallel to the z-axis. And let me use this picture here. Each of these vertical lines we see start from the ground and go all the way up until we hit the plane. Ground to the plane, ground to the plane, ground to the plane, all of them. All right, so that means because it's so consistent, that means we only need to do one integral, all right, to write this part out. And again, ground to the plane, so the ground is z equals 0, the xy plane. And then the plane up there was y equals 2z, right? So the plane was y equals 2z, so z is equal to y over 2. All right. Okay, what is the outer two integrals? Well, we think of the sun shining from above. That gives us all the regions where the shadow is going to be all the places where we actually need to have a vertical line, right, in order to fill up our region. And that's going to be, in this particular picture, everything here, and of course on the other side as well. All right. Okay, so it's going to be, let me draw it down here. It's going to be, so this is x, this is y, everything in here. Okay, so this this circle right here is comprised of the intersection of the cylinder, of our cylinder, with the xy plane, right? The xy plane is where z equals 0. Well, actually, our cylinder doesn't even have z in it. So yeah, our cylinder is just x squared plus y squared equals 4. And so immediately we know this is x squared plus y squared equals 4. All right. So our outer two integrals is an integral over a circle of radius 2. Okay. All right. And so this is essentially our setup, right? I'm not even going to write out the outer two integrals because one thing I want to emphasize is the outer two integrals, once you start doing them, right, it's just a two-variable calculus problem. So you don't even necessarily have to integrate with respect to dx and dy, right, when you get to that, right? You could integrate with respect to polar coordinates if you want, right? So I'm just going to leave it as a picture like this, and then once you've done the inner integral, you could, if you want, decide then to do a polar coordinate integral, all right? Or you can do rectangular, either way, whatever you're comfortable with, okay? Whatever the problem kind of forces you to do, or asks you to do, depending on what happens when you actually do the inner integral, all right? If you were to do a polar integral, right, then you would just go as usual. X and y would be converted to r d theta, right? And so you would be integrating, for example, in this case, r equals 0 to 2. This is a circle of radius 2, right? And then we're doing, filling this up with rays, starting from theta equals 0 to theta equals pi. Okay? So you don't necessarily have to set it up completely as a rectangular integral, xyz integral, straight from the start. All right. Okay, in fact, this is what we're going to be doing next section when we talk about cylindrical coordinates and spherical coordinates, where we have the option of integrating, again, in a different way. Okay, again, let's set this up in a different way. So let me draw a region again. So it looks like a wedge like this, right? And this down here is circular. We've got a plane up here, and we've got the cylindrical wall down here. And again, the bottom, the floor is the xy plane. Okay, so let's set this up with respect to dy. All right. Okay, this looks really weird. I'm going to redraw this. The perspective looks all wrong. So maybe that looks a little better. All right, so let's do dy first. Again, we're integrating 1. So this time we need to, again, look at x, y, z, rays along the y-axis, right? And this time, these rays are going to be starting at the plane and going out until we hit the cylinder, all right? Plane until we hit the cylinder, plane until we hit the cylinder, and plane until we hit the cylinder on the other side. Okay, so very consistent. So it's just going to be one integral. At least this part of the problem is going to be one integral. And again, we're always going from the plane, right, to the cylinder. Okay. All right, so what is the plane? Again, our plane is y equals 2z. Exactly. So just y equals 2z. Okay. Our cylinder was x squared plus y squared. So this was x squared plus y squared equals 4, right? So now this is going to be, the actual limit of integration is going to be square root 4 minus x squared. Okay. All right. It's the positive integral, positive square root, because we're integrating, we can see that this region that we're working on has only positive y's. All right, so we don't need to consider the negative square root. Okay. By the way, sometimes it's good to do a quick check to take a look at your limits of integration. They should definitely not have any y's in it, right? Because if they do have y's in it, when you do the outer integrals, you're not going to end up with a number because you're going to still have y's floating around. So something like y equals 2z, that looks okay. Y equals 4 minus x squared, that looks okay, right? Ending up with x's and z's is perfectly fine because our outer two integrals is with respect to x and z. Okay. All right, but again, ending with if you have y on the right-hand side, then you're going to be in big trouble. Okay, the outer two integrals, we have the sun shining along the y-axis. Its shadow creates the region of integration along the xz plane, right? What is that going to look like? Well, in terms of the picture, that's going to be something like that, right? So you can see that every point inside this shaded region on the xz plane is going to have a ray living above it, right? A dy integral living above it. Okay, so this point here corresponds to that ray right there. This point here, or that line segment, corresponds to that line segment here. All of the points in this shaded region correspond to a dy integral, all right? So we want to integrate our next two integrals with respect to the inside of that region. Okay, and again, this is going to be x and z, right? Because those are only two remaining variables. Okay, so what exactly is this guy right here, right? We're going to need to do it. We're going to need to know it because, for example, if we integrate with respect to dz first, we're going to be integrating from the ground to that curve, from the ground to that curve, from the ground to that curve. So we're going to need the equation of that curve in terms of x and z, all right? All right, so what exactly is that curve? Well, that curve is, when we look at the sun shining, right? That curve is the edge of the shadow, right? So what forms the edge of the shadow? Well, when the sun is shining, we can see that it's going to hit this guy here, that's going to hit the edge, right? Anything above that is just going to go all the way through, so we're not integrating there. Anything kind of below that, we're going to hit our region, and so we do want to integrate, right? So essentially the curve that we're trying to figure out is defined by this intersection of the cylinder with the plane. All right, so this is given by the intersection of the cylinder with the plane. What is the plane? The plane was y equals 2z. And our cylinder was x squared plus y squared equals 4, right? So the intersection, sorry, the intersection is going to be given by, well, both of these equations satisfied simultaneously, which means x squared plus 2z whole thing squared equals 4. All right. Okay. No more y's, right? So this guy right here, this curve is x squared plus 4z whole thing squared equals, or 4z squared equals 4. All right. Okay, so this one actually happens to be elliptical region. Okay. All right, but once we know this, we're all set, right? That means that if we want to integrate with respect to dz first, then we're going to be doing z equals the ground to z equals the curve. So the curve is going to be 4 minus x squared, whole thing over 4, square root of that, positive square root, because we're looking at in the positive, we're only considering positive z's in this picture. And where do we range from for the x's? Well, we need to do vertical lines starting from this edge right here, going all the way up to the other edge. Where are the edges? Well, or these endpoints here, they're going to be where z is 0. And we can see x squared plus 4z squared equals 4. When z is 0, tells me that x squared is equal to 4, which tells me x is equal to plus or minus 2. Okay, so that means these the outermost integral is x equals minus 2 to x equals 2. Okay. All right, let's do another one. Let's integrate f of x, y, z. I'm not actually going to do the integral, so it doesn't really matter. X plus y plus z cubed, right? Whatever. In the over the solid. Let me actually say over the region this time. Over the region that's above z equals square root x squared plus y squared, and below x squared plus y squared plus z squared equals 9. Okay. All right, so this is a solid region. The first guy here is a cone, right? So we want the stuff that's above the cone, and the second guy is a sphere. So above the cone and below the sphere. All right. So ultimately, we know our picture looks something like cone looks like that, right? And then below the sphere. So a sphere looks like that. All right. Obviously, this picture is not to scale, but as long as we get kind of a good idea of roughly what the thing looks like, we're in good shape. Okay. So roughly something like an ice cream cone. Okay. This bottom thing is the cone. Z equals square root x squared plus y squared. And then this top, I guess the ice cream is x squared plus y squared plus z squared equals 9. Okay. All right, so we set this up. Let's do this dz first. Triple integral, whatever our function is, x plus y plus z cubed, right? And again, our function could represent all sorts of things, but let's not worry about that for now. The last section for this week, we'll talk a tiny little bit about center of mass and stuff like that. But for now, just some function, and then we're doing dz first. Okay, so dz, where our integrals are vertical lines parallel to the z-axis. Again, essentially our integral is represented by what we get when we move z but have x and y be constant. Okay, I wanted to say it like that because next time we're going to be doing cylindrical and spherical coordinates, and when we integrate, right, just as we saw with polar coordinates, it's not going to be integration along necessarily lines, right? It might be integration along curves. So the kind of more careful way to think of it is always you have your inner integral, that variable is moving, the other variables are constant, all right? Whatever kind of curve you get out of that is what your inner integral is doing, okay? So in this example, it's just a straight line, right? Straight line, when z is moving, x and y are constant, you get straight lines, okay? Straight vertical lines. So we can see these vertical lines always start out at the cone and end up on the sphere, okay? So our integral is always going to be z equals the cone to the sphere, okay? And then what is that, more specifically, that's z equals square root x squared plus y squared to z equals square root 9, okay, 9 minus x squared minus y squared. And this is the positive square root because we're integrating above the xy plane, all right? Okay, the interesting part of this problem is the dy dz, or the other two integrals. So in this case, we have the sun shining from above. Well, as usual, right, dz, sun shining from above. What is the shadow? Well, the shadow here is actually going to be circular, or something, I guess at this moment, let's say we don't know. It's going to look something like a circular thing, perhaps, right? Or certainly something that's closed up, right? And we can see if we think of it this way, our shadow is going to be this inside region, right? Anything out here, the sun shines directly down, right? Which means there's no dz integral there. But anywhere in between, like here, we're going to have a dz integral, okay? All right, so what exactly is that shadow region? Well, we can see again from the picture that the boundary of this shadow region right there is determined by the intersection of the cone with our sphere. Okay, so basically it lives right above like this. All right. So this is why it's really important to draw the pictures, to know what the picture looks like. It really, really helps you figure out what these shadow regions actually need to look like. Okay, so it's determined by the intersection of the sphere and the cone, right? So what is that? Again, our sphere is x squared plus y squared plus z squared equals 9. Our cone is square root x squared plus y squared is equal to z. So the intersection is where both of these guys are true. Let's see. So this z is equal to x squared plus y squared, square root, tells me z squared is equal to x squared plus y squared, right? And so putting that into our first equation gives me x squared plus y squared plus x squared plus y squared is equal to 9. And so x squared plus y squared is equal to 9 over 2, all right? That describes our region. It's a sphere of radius 3 over root 2. Okay, so this this region out over here where we want to do our double integral is a full sphere, or circle, did I say sphere? Circle of radius root 9 over 2. So 3 over root 2. Okay. All right, and as usual, you can set this up however you like. Dy dx, right? That would mean we're doing vertical integrals first, and we would start from here to there for our x coordinate. If we want to do dx dy, then we would be doing horizontal integrals from down here to up there. Okay. I'm not going to set the rest of this up. Essentially, once you've gotten to this point, it becomes a problem from section 16.3, 16.4, or something like that. All right. What if we wanted to set this up again with a different order? So let's do dx first, right? And again, it might seem silly that we want to do dx first when in this particular case, the dz looked very straightforward. But again, it always depends on, ultimately, things depend on what you have inside the integral, right? It could very well be that when I try to do this innermost integral, I'm going to end up with something too unpleasant, and so I have to switch the order of integration, right? Or it could be after I do that integral, the next two outer integrals are too hard, right? So then you might have to switch up the order of integration. So always keep in mind that perhaps different orders of integration will actually work out better, even if it might not appear so at the very beginning, okay? All right, so if I did want to do dx first, my region is going to look like, again, it was like an ice cream cone, kind of, something like this, right? Actually, the sphere extends out this way, but again, just a relatively decent picture is good enough, right? We're only using the picture as a tool. Okay, if we do want to do dx first, this is x, y, z, right? We're representing our dx integral, We're representing our dx integral as lines where x is changing and y and z are constant. And so that's going to be lines parallel to the x-axis. And so we can see that's actually going to be a bit of a mess here. We're going to be doing from the cone to the other side of the cone, right? Actually, we usually want to write this as the limits of integration from a smaller number to a bigger number, right? So from x negative, from the opposite side of the cone to this side of the cone, right? Opposite side of the cone to this side of the cone. However, up here, we're going from the opposite side of the sphere to this side of the sphere, right? Opposite side of the sphere to this side meaning the side that's kind of facing us, okay? So this means that for this particular situation, we're going to have to do two integrals, right? So this one is going to be cone to the cone, and the second one is going to be sphere to the sphere. Okay. There's no escaping that because we literally have two different types of integrals as we look at all of these lines parallel to the z-axis. Okay. And as usual here, what is the cone? It was square root z equals square root x squared plus y squared, right? So that means the cone in terms of x is going to be z squared equals x squared plus y squared, right? So x equals square root z squared minus y squared plus or minus, all right? And that plus or minus is actually important here because we're integrating from the opposite side of the cone, which is minus square root z squared minus y squared, to this kind of the front-facing side of the cone, which is x equals plus square root z squared minus y squared. Okay. And we can do the exact same thing with the sphere, and that one's going to turn out to be x equals square root. It was radius 3, so 9 minus y squared minus z squared, negative, to plus 9 minus y squared minus z squared. Okay. Okay. And then, of course, whatever function we have in here, whatever function we have in here. Okay, so what about the outer two integrals? Well, we have the sun shining along the down from the x-axis, right, parallel to the x-axis. We can see that our shadow is going to be on the again on the yz plane, right? Because we're integrating with respect to y and z now as the outer integrals. It's going to be this guy right there, right? Where this guy here is essentially the cone, and this guy up here is essentially the sphere. All right. For the left-hand side integral, we were integrating just from the cone to the cone. And so for the left-hand side integral, it's only going to be over this shaded region down here. Okay. Okay, for the right-hand side, for the second integral here, it's going to be only the sphere part. All right? Because again, this part is only integrating from the sphere to the sphere. All right? So our cone here was a 45-degree cone. So this is y equals x. All right? Actually, I was integrating, sorry, I was integrating over the entire solid, right? So actually this should be, I should draw the whole thing. And up here, the whole thing. All right. Okay, this is y equals x, and this guy here is the opposite. So this is y equals minus x. All right. So if we were to set this up, probably it would be easiest to integrate horizontally first, right? From x equals minus y to x equals y. And then in order to fill this up with horizontal lines, we start at the ground and we go all the way up until we get to the intersection point of the ice cream cone, the ice cream with the cone, right? Okay, so where is that? So we figured out that up here, let's see. So we figured out up here that, so we can do this in many ways, but just a quick look here. We have x squared, oops. We have x squared plus y squared is equal to 9 over 2 at the intersection, right? We know that x squared plus y squared plus z squared is 9. And so 9 over 2 plus z squared should be equal to 9 at that intersection, right? And so z squared should be 9 minus 9 over 2, which is 9 over 2. And so z should be square root 3 over root 2. Okay. All right. So this height here is 3 over root 2. Okay. So z equals 3 over root 2. So we would be integrating in terms of our dz, z equals the ground until we get up to z equals 3 over root 2. Okay. And that covers this entire region with horizontal lines, the cone region with horizontal lines. And again, this is dx, oh, sorry, I guess, yeah. See, this is why it's always good to write the x equals the y equals. So obviously something has gone terribly wrong here because I've done x equals and x equals, right? But these outer two should be y and z's, right? So this should be y equals z, and this should be y equals z here, right? Because we're actually doing, our horizontal axis is y, not x. Okay, so sorry about that. Everything else looks the same. So y equals minus z to y equals z. All right. Okay, so, and we're doing dx, dy, dz here. Okay. All right, for the sphere, same idea. We're doing this red part, right? And again, we're looking at the yz plane. So if we integrate horizontally, or let's integrate vertically. I think that looks easier, right? We're going from z equals 3 over root 2 until we hit the sphere, right? So z equals 3 over root 2 until we hit the sphere. Okay. All right. What was the sphere? The sphere was x squared plus y squared plus z squared equals 9. We're looking at the situation where x is equal, we're on the yz plane. So x is equal to 0 here, right? And so this sphere, this circular part is z equals square root 9 minus y squared. Okay. All right, and where do we range from? We need to do vertical lines from this left side all the way to the right. Actually, I know this is a cone that's 45 degrees. So if the height is 3 over root 2, the width is also 3 over root 2. So y equals minus 3. Let me extend this a little bit. Y equals minus 3 over root 2 to y equals 3 over root 2. Okay, so there's often a lot of ways to figure out what coordinates certain points are at, or what curves, the equations of the curves. Whatever kind of is most convenient, just use that. All right, so again here, I knew that this was a 45-degree cone, and so if we just figured out this height was 3 over root 2, so that means this coordinate here has to be 3 over root 2 as well. Okay. All right, so again, this one we've decided to do x dz dy. So you can see that, if you do break it up in two pieces, you don't necessarily have to do the same order. All right, you just treat them as completely two separate problems. Okay, sorry if there's a jump right here. I stopped recording by accident, so let me continue. So our last example is swapping orders of integration. Let's say we have this problem here. So 0 to 5, 4 to 30 minus 2x over 5. And this one is 0 to 30 minus 5z minus 2x all over 3. dy, dz, dx. We're integrating something. And for whatever reason, we've decided dy, dz, dx is no good, right? Maybe the integral is too hard. Perhaps we want to try swapping the order of integration. Okay, so we're going to do this in the same way. We swapped orders of integration in two variables. We draw the region, and from the region, we calculate the new expression for the integral. All right, so we don't want to do it directly from just this expression here without the picture. All right, and just as with the two variable situation, it's very helpful to go from the outside in. All right, so what I mean by that is we're going to figure out the shadow first. Okay. All right, what is the shadow? Let's see. So the shadow is in terms of dz dx. By the way, I didn't put the y equals x equals. Oftentimes, like in the book, they don't put those there. So, just be aware. Of course, the ordering is given by the d's, dy, dz, dx. All right. So this is in fact y equals 0, z equals 4, x equals 0. All right. It might even be helpful for you to put it in, just so you get a literal view of what variables you're looking at. All right. Okay, in any case, we're doing the shadow. To draw the shadow is exactly a two variable calculus problem, right? So now we're just only looking at x and z, right, as the outer two variables. Let's look at the outer of those outer two variables, x equals 0 to 5. That means we only want to integrate from 0 to 5, so everything between these two lines here. All right, so our shadow is going to live between those two lines. Our inner integral for this this shadow region is z dz. So we're going to represent that with vertical lines. We can see that our vertical lines start at 4 and end at 30 minus 2x over 5. Okay, 30 minus 2x over 5 is a line. It's a line with negative slope. When x is 0, z is equal to 6. So it's like this, comes downwards like that, and we're integrating from 4 upwards. Okay, so our dz integral is represented by lines like this. All right. Okay, where does this line end up when x is 5? Well, let me actually write down here, x equals 0 corresponds to z equals 6, and that's how we got that 6 right there. And x equals 5 corresponds to z equals 20 over 5, z equals 4. Okay, so we actually know that in this picture, this line actually hits right there. Okay, so it's actually a triangular region. Okay, we're going from 0 to 5, so we're filling up this entire region. So again, we're integrating. Our shadow is this triangle right there. All right, so now we know when we figure out our entire region, x, y, z, if 6 is here, 4 is there, and 5 is there, we're only going to be integrating dy's in this direction along parallel to the y-axis. All right, and only above this shadow region, right? Everything, everywhere outside, we're not going to have a dy integral. Okay. All right. So the dy integral is going to be from y equals 0, so the ground, so actually literally from our shadow region, all the way up to this guy up here. So that guy up there is y equals 30 minus 5z minus 2x all over 3. And if we just divide the 3 to the other side, this is that. And then throwing the x and y's to one side, x, y, z's to one side and constant to the other, we can easily see that this is a plane. All right. So we're integrating from the ground to the plane. All right. Okay. So this particular plane. So we're integrating over the shadow region. So if we want to draw a picture, we kind of want to know where this plane interacts with this line right there, right? Or the line when we pull it out along the y-axis with this guy here and that guy there. Okay. All right. But looking at this, let me draw a picture again here. So our shadow region up there was z equals 30 minus 2x over 5, which is 5z equals 30 minus 2x, which is 2x plus 5z equals 30. Oops, equals 30, right? And if we look at this here compared to our plane, right, this was, let me draw it over here, x, z. That portion of our shadow region. Okay, we can see that this is exactly the same equation except with y equals 0, right? So what that means is my plane actually hits, literally touches this line segment right there. Okay, so which plane is it? Well, it's the plane that, if I were to draw the entire plane, it's the plane that when x is 0, when y and z are 0, x is 15. When x and z are 0, y is 10. And when x and y are 0, z is equal to 6. Right? So it actually looks like that. And what we've discovered is that this portion here, right, up here, we're integrating our triangular region, starts at 6, goes down to 4, and here's at 5, right? We've discovered that this portion here is exactly the same as that portion there. All right? So we're actually integrating this triangular top, kind of this, the tip of this tetrahedron here. Okay. So ultimately, our region is this upper portion of the of the full tetrahedron. All right. Okay. So in terms of our shadow, right, it would be something like right, something like that. Right. So we're integrating from here until we hit the plane. Here until we hit the plane. Okay. Maybe that's a little messy. Let me redraw it down here. Right? So Oops. Right? So we're integrating from our shadow region, right? Integrating out along the y-axis until we hit the plane, which is this face right here. Okay, always from the shadow region to the plane, shadow region to the plane. Okay, and it just so happens that in this problem, they all touch here, they touch here, and so it is actually just a tip of a larger tetrahedron. Okay. All right, now that we have that, we're pretty much all set, right? We can change the order of integration whatever way we like because, well, what is this plane? The one that's facing us, that's 2x plus 3y plus 5z equals 30, right? Again, this is getting a little messy. Let me just draw it by itself. Right? So this guy is the portion that's facing us. We have the ground over here. The ground is at height z equals 4, I believe. Let me see. Yeah, height is z equals 4, right? The height of this shadow right there is z equals 4. So this is z equals 4, right? And then the other two panels are just the coordinate planes. So this one right here, this panel on the left side, the back left side, is the xz plane. And this panel right there on the right back side is the yz plane. All right, so that's the full picture of our region. And with this, we can change our limits of integration whatever way we like we said, right? So if you wanted to integrate, for example, with respect to z first, right, you can see that the vertical integrals are going to start from z equals 4. You go up until you hit our plane, which is 30 minus 2x minus 3y all over 5, right, from right there. And then our dx dy integral is going to be the shaded region down here. Okay, so this is going to be that region right there, where this coordinate, let's see, I've drawn it up here. This coordinate is 10, that coordinate is 15, right? Again, we can figure these out in lots of different ways. This guy is 10, that guy's 15. So if we did it this way, our line would be, actually, was it 10 and 15? Let me take a look here. Sorry, that one's the x, that one's the y, right? So it should be 15 and 10. Okay, so this would be something like 2x plus 3y equals 30, right? Okay, and that's correct because, let's see, if we compare it with our equation of our plane all the way up here, right? If we let z equal 0, that should define the line that we're looking at right now. And so that's 2x plus 3y equals 30. Okay. All right, which means when we actually write out our dy dz, dy dx, let's do dy dx. So this would be y equals 0 to the line. So this would be y equals 30 minus 2x over 3. And then x equals 0 to 15. And then this would be dz, dy, dx, and then whatever function we're integrating. Okay. All right, so these problems can be quite a bit of work, but it's definitely the way to go to draw the picture. Start from the outside in, draw the shadow. It makes it a lot easier to figure out exactly what your region is once you've figured out what the shadow is. If your pictures do look indecipherable, just draw another picture, right? I've done it many times here, right? Sometimes my pictures get a little messy, so I just redraw the picture with just the relevant information, right? Do that a lot. Don't feel like you have to just work with one picture because things are just going to get really messy once you start shading stuff in and stuff like that. But yeah, these problems can get quite involved. So try to do as many of them as you can so that you get really used to kind of visualizing things or drawing things in 3D. It'll really help. Actually, even for the next section where we do cylindrical and spherical coordinates, where you again you have to visualize things.